Okay, this is going to be the lab report for Physics 2212 Lab 2, where we are going to revisit Lab 1, which was charge tape. In this lab, we're going to look back at the previous charge tape lab by more accurately analyzing the real-world physics of charge by looking at things as a dispersed charge rather than a point charge. To do this, we're going to create a more advanced computer model in GlowScript to calculate electric force compared to what we did last time. The results of this, we found that the charge on the tape is going to be 2.5 times 10 to the negative 8 coulombs. The force of the electric field is going to be 2.118 times 10 to the negative third newtons. And the magnitude of the force of gravity is going to be 2.18 times 10 to the negative third newtons as well. There's some key principles to understand for setting up the code for this lab, one of which is Newton's second law, which is force equals mass times acceleration. Also, we're going to need to know Newton's third law, which I improperly labeled here as Newton's second law, but that is going to be every force has an equal and opposite reaction. We're also going to need Coulomb's law, which you can see written out there, which is Q1 times Q2 over 4 pi epsilon naught times r squared. And we also need to understand that like charges repel and opposites attract. In the original lab, we found the charge, or we created a charge on the tape by sticking a tape on top of another and then quickly unsticking them, which creates a charge. We're going to need to determine the charge of these objects by bringing them close to one another and figuring out what sort of charge they are relative to a known charge. We test the force of these by bringing them together, and you can see that they repel. We can also know that they are positive as a result. And we'll use this data to calculate the charge. In this lab, we've got a few key assumptions. We're going to assume that there's no air resistance, even though there will be, and that the charges are equal, even though they are very unlikely to be perfectly equal. We also know that we're going to have some sources of error because some data is found via an approximation and rounding. But we're also going to have outside systems affecting the charge because the charge will not be perfectly stationary. It will be constantly changing. And there's also going to be human error involved. The system here is going to be the top U-tape, and the surroundings are the other U-tape and other objects in the room that have a charge that are going to affect these. And the initial conditions are, we're going to assume that they start with a neutral charge, even though they likely don't. We're also going to assume that they're equal in size. Here you can see the code where we find the force on the top U-tape and then the force on the bottom U-tape. We will now and then here you use the data found here to help create the vectors that are simulated here in the actual computer model. The prediction will be that the tip will be repelled by the other, causing it to float. And the observation was that it was indeed caused to float when the tapes were approximately 5/10 of a millimeter away from each other. We see that both models show the tape to float when the other came nearby, but the difference is that they needed to be closer in the model, and we also need the resulting force is also a lot weaker than anticipated. What if the model had the charges as a single point charge? The tape would have a lesser charge and resulting force due to electric field. The magnitude is lesser than the magnitude of the charge we assume to be a point charge because the charge is spread out over a large area instead of just being one single point. And why do these differ? This is because, like I said, point charges are simulated. There's nothing around them, and line charge is spread out over an area, which would cause this to be the more realistic of the two charges. Because in real life, point charges aren't necessarily a thing, and the line charge would be closer to what you would expect to actually see.